Hello, everyone. Welcome to our IOMP webinar. As you know, the title is Meet the Industry, Unlocking Radiotherapy's Potential Through Innovation. So today we have two distinguished speakers, Dr. Daniela Eulenstein from PTW and Dr. Khee Looe from LAP, who will be sharing their expertise with us on solutions for quality assurance and surface-guided radiotherapy. So the topic today is about radiotherapy and some novel tools and solutions. Both companies are IOMP's corporate members. LAP is one of the world's leading suppliers of systems related to laser projection, laser measurements, and other processes related to lasers. And PTW is also one of the global market leaders for dosimetry solutions in radiotherapy, in radiation therapy, radiology, diagnostic interventional radiology, and also other areas such as monitoring, radiation monitoring, metrology, and so on. I guess most of you are familiar with the products of those companies. So I will start by, and I would also like, I take the opportunity to thank Magdalena Stoeva. Professor Stoeva, as you all know, is the IOMP Secretary General, the organizer of this webinar. I will only moderate the webinar, and she's behind the scenes. So yeah, thank you, Magdalena, and I will start with Dr. Eulenstein. She will be discussing the Ruby modular quality assurance fandom and its application on in online adaptive radiotherapy. The title of her talk, Ruby, the modular QA fandom meets online adaptive radiotherapy. Just a few words about Daniela. She has a master's degree in physics. Both speakers are colleagues, medical physicists. And we are happy that medical physicists are involved in research and innovation and novels in industry. Daniela has a master's degree in physics, a PhD in medical physics. She worked as a medical physicist at the radiotherapy department of the Pius Hospital in Oldenburg, Germany. And she works at PTV, is currently working at, works at PTW, PTV, right? This is the German pronunciation. So works at PTV as a research scientist, part of the team, the product management team, and Daniela is responsible for the Ruby fandom, right? So you are the right person to present this tool. Daniela, the stage is yours.
Thank you very much. Thank you for the introduction. So I will share my screen and turn off my camera. So let me share my screen. Okay, yeah, so I will talk about our PTW Ruby solution, the Ruby adaptive solution, our end-to-end testing tool for adaptive radiotherapy. I would like to start with a short introduction of the citation. It's quite old, 1997. From Jan et al. So adaptive radiotherapy is a closed-loop radiation treatment process where the treatment plan can be modified using a systematic feedback of measurement. You see, it's quite old, but nowadays adaptive radiotherapy is quite modern, and so also in 2019, they discussed the time point of adaptation. And of course, adaptation in principle can also be offline. This means the adaptive plan is prepared in between fractions. So we change the treatment plan between two fractions. But today I would like to talk about online adaptive radiotherapy. And this means the adaptive plan is generated immediately before fraction based on in-wound imaging. And the very modern therapy is based on, or mostly based on CT based online radiotherapy. So the Varien ETHOS, for example, is a very, I think, very famous example for adaptive radiotherapy. And with this, we have a new demand on QA solutions. So for different parts of adaptive radiotherapy, we have to think about new solutions, new phantoms about or for radiotherapy in this field. And so I would talk about today about our Ruby phantom. So the Ruby phantom consists of different parts. So we have different base systems. You see here this standard base phantom, also a head-shaped phantom. And then we have 7 different inserts. So electron density, different electron density materials, a linear QA insert, patient QA inserts, system QA inserts, and our adaptive solution. And all these inserts we can combine with different add-ons. So for the electron density insert, for example, different electron density materials, different metals, and so on. Then for the patient QA and system QA solutions, different detector holders and a tilted base. And for the adaptive solution, here we call it organ sets. You see it's a quite large phantom family, but today I would like to talk about these things here. So our Ruby adaptive solution. This I would like to start with our base phantom. So for our adaptive solution, we have to understand or have a look to our lines here. So we have this phantom, it's made of polystyrene, and then we have different lines. So of course the central marking, so the black line is the central marking, here the CT marker. And then we have 2 different lines. And with these 2 different lines, we can make a defined displacement of the phantom. So translational shift using the gray line, or a rotational and translational shift using the red line. And the red line has to be paired with combined with the Ruby tilted base. So the Ruby tilted base is a little plate which you can combine with the phantom, and then we have a defined rotation of the whole phantom. And now we can combine this with this insert here. This is our adaptive insert, and so it can be click in this base phantom, and then we have the whole set. This insert is introduced or was introduced last year. It's a very new insert, and the idea is that we have the insert here has an opening, and this opening we can put in so-called organ sets. You see here 2 different organ sets. So far we have our prostate A and prostate B organ set. Both organ sets consist of different human-like organ structures. So bladder, rectum, and prostate. You see here the yellow one is the bladder, the orange one the prostate, and the black one the rectum. And you see in these 2 different organ sets, we have different shapes and different volumes of the organs. For example, the bladder, here that we have a full bladder, and here an empty bladder, and so on. The organs are made of high quality tissue equivalent material. So for prostate and rectum, we have an ICRU muscle material with a density of 1.07. And for the bladder, we have a density of 1.05. So the idea was that we have realistic Hounsfield units. So that it's comparable to a human human bladder or human prostate. And for me, it's important to say that only CT visible, not MRI visible. So this phantom at the moment is only visible in CT, so especially for CT-based online radiotherapy. And in the end, we can also position a detector in each organ. So you see here little holes. So you can position here in Simiflex 3D ionization chamber in the prostate, or in the rectum, or from this side also in the bladder. So you can perform a dose measurement in these human-like structures. Now I want to give you an overview of the possible workflow of this phantom. So my example is from a Varien ETHOS system. So an end-to-end test with this system at an Varien ETHOS. So we start with our Ruby phantom combined with this new insert and the organ set A. So we make a CT, our reference plan, organ segmentation and so on, make a PTV, and then we make our reference plan. Then we go to the machine, so to the ETHOS, and now we switch the organs. So now we have organ set B, and we combine the phantom with the tilted base and align it to this red line. So now we have a defined misalignment here and a defined rotation in our phantom positioning. Next step is the auto-segmentation. So the system will make a chromium CT of the phantom. So here we see the chromium CT. This is the reference CT. And now we have to contour the organs, or the AI will do this, and we have to change this AI result. So we need the new segmentation of this new chromium CT. And then based on this chromium CT, the system will make the plan adaptation. So now we have our new treatment plan, so the adaptive plan. And in the end, we position a detector in the phantom and we can measure the dose. So you see, you have the whole treatment chain tested using this Ruby phantom. And I would like to go in detail to every step. So here, the first step, the treatment planning, looks like this in the ETHOS system. So this is the TPS from the ETHOS. Here you see an IMT plan on the prostate. So the prostate was contoured, so our CTV and then a PTV, and then here the rec. You see a standard treatment plan. And you also see here the CT marker. So in the end, we want to measure the dose. That means we have to calculate the dose at the point where we measure. And these CT markers here indicates the point of measurement. So here you see the CT marker, and here is our point of measurement. And now it's in detail in this ETHOS TPS system. So you need a structure to export the dose, and you need the PTV structure. So here we made a PTV in the center of the CT marker. So call it Simiflex 3D. So the idea is here is the Simiflex 3D structure, and it's also a detail for the ETHOS system, or maybe here are some ETHOS users, so we can make a D-mean, so mean dose constraint, and with an R priority, so it's only for documentation. And using this tool here, you can calculate the dose in this little PTV structure, and you only document this dose. Okay, then the next step is change the organ set. You see it here. It's quite easy, very fast. You can remove this organ set and switch to this organ set, then click the insert again to the phantom, and here you see we positioned the phantom on the tilted base. And now this is a very hard task for the system, because now we have a different organ structure, and we have a shift in our phantom and a rotation. So now our theoretical patient, the Ruby patient, everything is different. The organ shape, the organ volume, and we have a shift. And now we start this plan adaptation process. Here you see the CBCT. Again, here the CBCT. So here you see the tilt and this new organ volume. So this is the reference CT, and here the CBCT. And this is in the end of the contouring process. Honestly, the AI cannot contour everything 100%, so you have to change it manually. But as far as I know, it's standard also for real patients. So here you see the final contouring of the organs. And next step is to shift this PTV. So because again, we have our shifted phantom, and the system cannot find the PTV position correctly for this chamber. So again, this is this chamber PTV, and same procedure. Here we have our CT marker, and here's the chamber volume, and this has to be done manually. But the idea is that also in this adaptive plan, we have our chamber volume, and this is positioned aligned to the CT marker. Yeah, our chamber position. It's important because you need a workflow to extract the dose at this point, and therefore please use this chamber PTV. It's quite easy. Okay, next step, plan adaptation. So here we see the result. So the system calculates a completely new treatment plan for this new configuration. So here we see the tilted phantom, and this is the new organ configuration. And this is the new plan. And now we want to measure this plan. And for this, we position a Semiflex 3D chamber here into the Ruby. At this photo, we only do this at the prostate, but of course you can also position it on the rectum or on the bladder where you want. And so those measurements can be performed. And if you have here Unidos Tango, for example, you can use your iPhone and measure the dose. And then you can compare this to this result of this PTV. Here we have again the PTV, the Semiflex 3D PTV, and you can now compare the dose here from the adaptive plan to your measured dose. And using this workflow, you have a very detailed but also fast workflow for an end-to-end testing at the adaptive radiotherapy system using this phantom. And yeah, I would say it's quite nice. So in cooperation with two reference sites, we create an application brochure about this workflow. So you can find this on our website, so ptwruby.com. If you scroll down, there's an area with get more information, and here you find this Ruby adaptive radiation therapy brochure. And all the steps I showed you are described here. So it's an introduction. We also make an so-called planning directive. So it's like a template for the ETHOS TPS. So you can download here the template and import it to your system. And then you have a first structure for your end-to-end test treatment plan. And you see many screenshots and a very detailed overview, I think, for your test. And at this point, I would like to thank our reference site. So with me, it's the authors are Dr. Künzel and Mr. Grauer. Dr. Künzel worked at the radiotherapy department in Berlin in Germany, and Mr. Grauer in Hamburg. And with these two sites, we create this brochure. Okay, I come to my last slide. So I give an overview about our Ruby adaptive system. So for online adaptive radiotherapy, we have a new need for QA equipment. We need a phantom which enable anatomical changes. And with the Ruby phantom, we create such a phantom. So the Ruby adaptive insert enables different anatomical structures and enables end-to-end testing in adaptive radiotherapy. And yeah, this was my last slide. I would say thank you. Please type in all your questions, comments in the chat. And yeah, I'm glad to answer everything. And if you want to contact me, please write me an email. Okay, thank you very much.
Hello. Well, thank you. I was disconnected for a minute, so sorry about that. Many thanks for this excellent presentation, Daniela, and I'm happy to inform you that we have more than 1,100 participants, which is great. It is really a very interesting topic, and many colleagues have joined the webinar. So our next speaker is Dr. Looe. The title of his talk is LAP Luna 3D Surface Guided Radiotherapy System. A few words about Dr. Looe. He's the deputy head of medical physics at Pius Hospital in Oldenburg, Germany. He's a scientist in the medical radiation physics group at the University of Oldenburg. And as a part of this working group, he has clinical research and teaching tasks, activities, and he is working on surface-guided radiation therapy and works with a Luna 3D SGRT system from LAP. So Hui, please, the floor is yours.
Okay. Let me share the screen. So thank you again for the introduction. I'm very glad to be here today. And thank you to IOMP and LAP for inviting me to share our clinical experience with Luna 3D, the new SGRT system from LAP with you today in this webinar. So this is my disclosure. We are actually one of the first clinical installation sites of Luna 3D. And since the first installation, we have been working closely with LRP in testing and in evaluating the clinical workflow with Luna 3D. Before I start my presentation, I would briefly like to introduce our institution. So the Clinic for Radiation Therapy and the University Clinic for Medical Radiation Physics at the Pius Hospital is part of the University Hospital in Oldenburg. So we engage in clinical as well as teaching and research activities. Clinically, we operate 3 Elekta linear accelerators, 1 Synergy and 2 Harmony Pros. Our institute has actually maintained close partnership with many industry partners, and actually we are very happy to be the first clinical installation site of the LUNA 3D system. So in the past year, actually, surface-guided radiation therapy, or SGRT, has evolved into as a standard of care in modern radiation therapy. And LUNA 3D from FIP is a new player in the field of SGRT. But first of all, why do we need SGRT? Among others, SGRT could offer high precision and efficient patient positioning without applying additional dose to the patient. It also enables dose-free patient monitoring, allowing advanced online motion management, for example, DIBH. It can also provide higher patient comfort by eliminating the need for markers or tattoos on the patient. And one also has then the possibility to reduce uncomfortable patient fixation, for example, masks. So SGRT is actually more than replacement for lasers. In contrast, I think this system can do much more actually in the coming years. So why LUNA 3D? After using LUNA for some time, we think that LUNA offers some unique features that I want to emphasize here. So first of all, LUNA 3D is very easy. I know that many clinics have concern of the learning curve in introducing a new SGRT system. And I think it is true that implementation of SGRT system in the clinic requires tremendous team effort, and more importantly, also the willingness to embrace the new technology, especially when we know that the lasers have been used for a long time. But I think the simplicity and, more importantly, the very intuitive browser-based interface of LUNA 3D could really help to overcome these challenges at the beginning. The system is also very fast, using GPU parallel computing that guarantees very high performance with very large field of view and very high frame rate. And lastly, one of the features that actually we like the most is the virtual lasers, as shown here on the right-hand side. And this feature is really cool, and I will explain a bit later why this is the case. So currently we have 3 LUNA 3D systems installed in our hospital. So the first installation was actually already in June 2023 at an Elekta Synergy accelerator. We have also now the LUNA installed with 1 port at our new CT last year. And we have also 1 new installation plan in the coming weeks. So since the beginning of our journey with LUNA 3D, our RTT team has been involved in the clinical evaluations and implementations of the system. So we had some useful on-site trainings here with Wolfgang to give our RTT first-hand on practice with the LUNA 3D system. We also had actually a great and very fun training at the headquarters of FIP in Oldenburg some time ago with the whole team of RTT. As you can see here, it was really very nice, very fruitful training for everyone. So from the physics perspective, of course, we also need to ensure that the accuracy as well as the reliability of the LUNA 3D system before we proceed with the complete clinical implementations. So we have been performing actually a lot of testing and measurements with the LUNA 3D system since the first installation in 2023. And some of these tests were performed based on the recommendations in the ASTRO guidelines on SGRT systems, including static accuracy, dynamic accuracy, as well as a very comprehensive end-to-end testing. In the next slide, I will present to you some of these results we got. So firstly, the static accuracy test. So this is actually a very simple test, but also important. So we actually use just our daily check routine with the pentaguide phantom. So what we did was we first aligned the phantom to the room lasers. So as on the left, and then on the right, you could see already the agreement between the lunar 3D measurements as compared to the external structure derived from the CT scan of the phantom. So after the alignment, so on here you could see this offsets value, the 60 offsets values. And take note that these values are all given in millimeters. So all these are actually well below 1 millimeter. And to test the translational and rotational accuracy of lunar 3D, we use the Ruby phantom. We have heard about this phantom in the previous presentation from Daniela. So what we did was, we first positioned the Ruby phantom correctly. So as shown here on the left side or upper left picture. And then we capture a reference of this position. And then we could reposition the phantom with a predefined translational and rotational arrows, as shown here in the lower left figure. And then we could compare the measured values, the 60 values from lunar 3D to the expected values. And you could see the differences between these two, smaller than 0.54 millimeter and 0.1 degree. So actually very good results as well. And then we also did a lot of dynamic tests. So this is one of the dynamic tests we conducted using the CS dynamic lung platform and with the EasyCube from LLP. We have tried different motion patterns, different amplitude, different frequency. Shown here is one of the extreme cases where the EasyCube, as you could see here, was moved like up and down with 1 centimeter amplitude and 1 second per cycle, so 1 hertz. So it's actually a very fast movement. And here below, you could see the real-time recorded movement with lunar 3D. And here above, you see a zoom in of this registered spatial and temporal movement registered by Luna, which I would say hardly distinguishable from the actual movement of the phantom. So the dynamic performance of the Luna is also actually excellent. And one of the most comprehensive tests we did was the end-to-end testing as recommended also in the ASTRO guideline. So shown here is actually our current end-to-end workflow. So we start with the CT, and then the data will be imported to the treatment planning system where the treatment planning is performed, involving registration, isocenter placement, optimization, dose calculation, and so on. So once this plan is ready, so it will be exported to our record and verify system prepared for the irradiations. And at the linear accelerator, the phantom will be positioned with the help of cone beam CT. And after the necessary couch correction, so the plan will be delivered and we measure the dose and compare the dose to the expected value calculated by the treatment planning system. So we have to actually adapt this workflow to incorporate the positioning workflow using lunar 3D as shown here in red. So the red are the additional steps we built in. So the main difference of this SGRT end-to-end testing workflow from our current one is that the positioning is completely performed using lunar 3D without lasers. So the room lasers will not switch on during the entire process. So in other words, we are not using any markers to position the phantom. So we use also the Ruby phantom for this end-to-end testing, as we have been using for our current testing as well. So because we are not using any markers on the phantom, we are not positioning the phantom using any lasers. So we could set our isocenter at any point within the phantom. So we just put it here as shown in the arrow, by the arrow. And then we prepare the plan and then export the plan and prepare it in the lunar 3D software. And at the LINAC, then we just align the phantom with the help of lunar 3D. So not using any lasers. So we align the phantom so that we have almost perfect values here as shown by Luna. And then after that, we perform a CBCT of the phantom. And the results are shown here. So I think we can agree that the results are very acceptable, well within the tolerance level recommended in the ASTRA guideline. I also want to note that this is an end-to-end testing. So the results here do not only show, let's say, the accuracy of the LUNA 3D, but it reflects actually the total uncertainty of the entire workflow up to this point, including the planning, CT, the laser, and the KV isocenter or the CBCT isocenter congruence, and also the registration itself. So we still have actually very small errors here. So after that, of course, the last step was to irradiate the plan and to measure the dose. And in this case, we had, as you could see, agreement of 1.2%, which is also very good. So in the next few slides, I want to show you some clinical workflows with LUNA 3D. The first step is the patient preparation. So it starts with the export of the DICOM data from the TPS. So the RT plan and the RT structure from the TPS, and then import this data into the LUNA 3D software. So all the demographics will be imported automatically. And then the imported RT plan and the this external structure will be assigned to a treatment cost, for example, breast right or prostate or whatever we are going to irradiate for that particular patients. And after that, one would need to draw a ROI, so the region of interest. You could see here how it could be done. You can see the reference surface imported, and then what you could do is just draw the reference at ROI. ROI is used for the registration, so it means that the system monitor this region defined by the ROI. So in this case, a breast right irradiation, so we just kind of define the ROI in this way. So you could see it's very easy. And after that, if necessary, you could still edit some treatment steps, but normally you do not have to do that. Everything's done automatically. So with a bit of practice, this can be done within 1 or maximum 2 minutes by our RTT. And then after the preparation, then we can actually start using LUNA to position our patient. And I think this is also the best place now for me to showcase the visual lasers concept that I mentioned at the very beginning. I will actually show you a recording of a real patient positioning. And let me pause for a second and let me start again. Let me pause for a second and let me try to explain what we are seeing. Oh, I'm not sure why is it jumping. Sorry for that. Okay, as you could see, there's a purple surface, and this is the reference surface of the patient, and the green surface is the real-time LUNA 3D measurements. But what we really need to focus now here in this case is on the red and blue lines that are projected on these surfaces. So the red lines, they are the room lasers. So you can see them as room lasers indicating the isocenter of the room. So they are not moving, they are stationary. And then these blue lines, they are like markers on the patient. So they move along with the patient. So what our RTT needs to do actually is to just match the blue lines to the red lines. So you could see that this patient has a slightly rotation, like your rotations, and our RTT can actually easily identify this rotation and correct this. And you also see actually how sensitive and how fast the system is responding to what our RTT is doing. So the RTT is moving, correcting the rotations. And so working with these visual lasers actually mimic the workflow of traditional lasers, but without the need for us to mark the patient, to do any to do any markings on the patient or tattoos on the patient. And our RTT really loves these features, so they use this actually every day or for every patient. And you could also see how fast our RTT could position the patient. Everything in this video is less than 1 minute. I think it's like 40 seconds. So this is the positioning of the patient. And I'll let you watch this video one more time. So without me explaining. So it's done. So that's positioning. So you see the lines match, and you have here on the left actually very good 60 offset values. And this is another example. So as seen earlier, once these two sets of lines, they match each other, the lines will turn into white, indicating that we have actually a good positioning. And of course, then during the irradiation, Luna 3D also monitors the patient for us. So this is another example. This is a prostate case. And you could see also here the visual lasers, and you could see the real-time 6D values. And in addition, you can also see below here, like the log of the real-time monitoring over the entire fraction. So you could see that the patient is lying actually very stable during the whole radiation in this case. So lastly, I want to show you the DIBH workflow. I could not show you with the real patient here, but I would just demonstrate it using a phantom simulation that is actually very similar to the DIBH workflow. So the phantom, so we use also the CS dynamic lung phantom, and now the program is, the phantom is programmed to simulate actually a free breathing pattern, and then followed by a DIBH, and then after that, the free breathing and so on. And this is actually what we get. Let me pause the video for a while, just explain you. So on the left side, this is the iPad that we use as a remote control. So it comes with the system. So this is the control the RTT can use in the treatment room to look at this information. In addition to the big monitor that we have as well, that could also change the setting and do some editing here. And then on the right-hand side, we have this iPhone that acts as the patient coaching device. So this is what the patient would see. So this is mounted in front of the patient during the irradiations. So we start the video again. You could see that during the free breathing, that's what the system is recording. So you will show you this free breathing pattern. You could see now we are still far away from DIBH workflow. We have still a large error here, but this is expected. And this is what the patient is seeing all the time. She's getting a feedback of her own breathing. But when you say she's ready, she'll just breathe into these windows. And then you could see that we are now in the DIBH phase, and then the values are all green here. We see that we are now, we could now start, for example, the irradiations. And then we could monitor this all the time. The patient will try to hold this position as long as possible. But once we see that, okay, she could not hold this position anymore, so we get directly a signal the patient is leaving this DIBH breath hold, and then we could stop the radiation. Then she would just start breathing normal again. And then after some time, so that then she could try to do that again. So this is how it works. So the patient gets a very simple feedback, what she needs to do. And we could see from outside or from our screen, like monitor the whole process. So lastly, just want to quote what our RTTs said about Luna 3D during our clinical evaluation and implementation phase. And I really assure you, these are real quotes from our RTT. They told me this. I just translated this from German. So what they say, once you understand it, it is incredibly easy to use. And it works perfectly. We are avoiding some unnecessary cone beam CT repetitions now, because we could correct these rotations very easily with Luna 3D. And I also heard that they said we can actually set up our patients with Luna 3D faster. And you could see in that video, if you know how to use the system, you have experience, it is really easy and fast. So I hope this presentation has been helpful for you in getting to know Luna 3D a bit more. And if you want to know more, I have this QR code here that leads you directly to the website of the Luna 3D. So thank you very much.
Thank you, Khee, for your excellent presentation. Both presentations were great. And we have some questions and some time. So I will start. Questions have been selected on a first come, first served basis. So we'll start from Daniela. by the way, I read the questions from the Q&A feature of the Zoom platform. So I didn't have any, I don't have any idea about chat and what has been expressed via chat. Daniela, can you swap the organs between sets? For example, bladder from set A, prostate and rectum from set B?
Each organ, no. Organ set means we have one block, and in this block we have prostate, bladder, and rectum, and then you can remove this block and take the other. So we call it organ set. So you have two blocks, organ set A and organ set B. So it's one combination of bladder, prostate, and rectum, and one other combination of bladder, rectum, and prostate.
Thank you, clear. And I think there is another one question related to the same. Will other organ sets be produced in the future?
What? Film insert?
Yeah, organ sets. Other organ sets.
Other organ sets.
Yeah, other
yes,
organ sets.
Yes, I can say yes, but I have no time scale. But yes, so this is the idea of this insert, this modular insert, so that we have one insert and different organ sets. So of course, other organ combinations are possible. And I think it depends on the field of adaptive radiotherapy. So as far as I know, prostate is a very famous example for adaptive radiotherapy. Maybe, yeah. So prostate and or the bladder region. Maybe in the future there are other regions, and of course we can create other organ sets for other regions.
Okay, and is there any plan to offer a film insert for Ruby?
I
guess for dosimetry.
Yes. So in principle, we have a film insert. So there is already a film insert for Ruby. It's an homogeneous insert where you can put in a radiochromic film. And I also know that there are customers, they want a combination of film insert and organ set. We know this, and at the moment I have no time scale, but I know that's interesting to combine it, film and organ set.
Yeah. Did you look at organs, those simulated structures that could be variably filled? For example, a bladder that is connected to a syringe.
Yes.
Our colleague says to have any volume from full to empty. So,
yes. So me as a medical physicist, I also want to have this. Of course. But Ruby is a medical device. And with all the paperwork, and we have, of course, an CE mark, FDA, and so on, it's not so easy to make this, or to have a solution for this variable organ principle. So therefore, we start with two different sets. So at the moment, we have only two combinations. But yeah, it works, and of course, more is better. But yeah, give us some time.
Yeah, certainly. And there are questions about the cost and about about training. So can you give us an idea about the cost, and also if there are training courses for medical physicists?
So cost, no, I cannot. So please contact the PTW subsidiary in every country. I'm not a sales person. But for training, so of course we have our education and training team, we have application specialists, and we have the dosimetry school. So we have one dosimetry school, which is it's for Varica and Ruby. So of course I can recommend this dosimetry school. So I would say we have training courses for Ruby.
Okay. Other questions? Do you have a system like that for protons or hadrons?
In principle, you can use Ruby for protons. Please have a look at our website at this area. I showed it in the presentation, get more information. There is also a brochure about Ruby and protons with another insert, but in principle, you can use Ruby for protons.
Thank you, Daniela, for this discussion. We have to move to Khee presentation and questions to Khee. So one question is, what is the maximum angle allowed for the correction of pitch deviation, which could be corrected from the console?
The correction is done still manually, so Luna 3D can actually like measure these rotations in all different directions. And if you see this rotation as I have shown you, so basically what you do is you try to really like rotate the patients, do the corrections on the patients, so that you get very, very small values in these rotations. And then you do the radiations. Maybe you're asking about the couch corrections, so automatic couch corrections, if these values could be corrected by the couch automatically. Currently, it's not possible because of the interface between the accelerator and Luna 3D, which will be coming in the next. I'm not sure exactly when, but very soon. But then how much you would be able to correct also depends on the devices you are using, the couch and the interface.
Yeah. Again, I'm trying to select questions on a first come, first served basis. So another question is, do you have a plan to make a Ruby insert for upper abdominal organs, pancreas, and organs in that area, the surrounding organs?
So an official plan, no. But yes, there are some users, they wish pancreas, we know this. But again, I have no time scale, but in principle, it's possible, of course.
Yeah, there is a colleague says he or she doesn't understand the virtual laser in Luna. How the system knows, the question is how the system knows the position of the room laser during the CT.
Yeah, good questions. Maybe I did not explain it well enough. So basically the Luna system is calibrated, of course, so to the room isocenter. So Luna 3D system knows actually where the isocenter in the room is through a calibration process. And then the isocenter in the patient itself is derived from the plan. So you send this plan together with the surface to Luna, and Luna then knows, okay, for this patient, the isocenter is in patient at this position. So then what we see is that, and it will be shown as blue lines on the patient surface. So what you do is you just move the patient until the blue lines, they coincide with the red lines, and which means that you are placing the isocenter in the patient to the isocenter in the room, or like matching it to the room isocenter. And by doing so, you're just placing the patient correctly under the machines.
Thank you for the clarification. We still have 2-3 minutes, so I will select now because we have more than enough questions. So one question is, could you please tell us some basic differences or advantages of Luna from Visionaries?
I cannot, because I have not used Vision RT personally in a clinic, so I have seen this system in use. So I think both are actually good systems. I would say both actually works. They are both good SGRT systems, but Luna is new. So it's based on a more modern architecture in the hardware, in the software. And it gives you, that's why we have the possibility to provide a very large field of view. As you could see in some of these videos, we could really see the patient from the head to, I don't know, like you can see anything you would like to see in real time, and everything with a very high frame rate. And so this opens actually possibilities for very like interesting applications in the future using Luna 3D as well. And I think this is what we like. And I think that this concept of virtual lasers that projected on the patient, like the whole patient, also very useful. I think this is a unique feature of Luna 3D. There would be some other differences, definitely, but as I said, I don't know, cannot elaborate on all these differences. But for me, these are for me, these are the two very big advantages of the Luna 3D system that we like actually very much clinically.
Thank you. Last question related to Luna 3D. Can Luna 3D hold automatically the beam while the off position is out of tolerance?
Not yet, because it depends on the interface to the accelerator. So we'll be testing this interface in soon. And so, but the plan, as far as I know, that this interface will be introduced so that the Luna could then perform like beam hold automatically or beam on, and additionally also this couch movement. So this Luna could this measured offsets by the Luna could be then sent to the accelerator and to be corrected automatically, just as I think other SGRT systems.
Well, I'll try to utilize the last minute with another question. While you are talking, I'm trying to. So, based on your experience, Luna 3D, can Luna 3D reduce the work time of radiographers, radiotherapy technologists, medical physicists? Do you have any estimate? Do you have any idea about the workload reduction or work time?
Yes. As what, like according to what I have heard, like in some situations, our RTTs said really that they could now set up the patients faster, and because they know exactly what to do. So just by looking at these representations of the positioning, they know what they need to do exactly. So they are just doing what's necessary to correct the patient positioning. So they are very efficient. And that is one aspect. And the other aspect is that because they could now correct for rotational errors before we even start a CBCT. So we have in the CBCT now for these our patients like very small errors, so that we do not need to do these corrections after the CT. So we could, if you do not have 60 couch, and normally if you have a big rotations, you have to go in and then we do these rotational corrections and then do a CT again and hope that everything is much better. But now for some cases, we are saving this additional CT. So because we have already small rotational errors, and because of that, we are saving actually a lot of time. And not only of that, we are also saving a lot of additional dose for patients in the patients. And that is also actually from a medical physical perspective, very, very interesting or very useful.
Yeah. Okay. There's a question that needs seconds to be answered. How many cameras do you use?
Depends. So for the accelerators, for C-arm accelerators, I think the standard configurations, there are 3 ports, and in each port there are 2 cameras. And I think for closed bore or for bore type of Linac like Halcyon, ETHOS, The standard configuration is with 4 ports, so one from behind. And there's also this 1 port configuration normally used at a CT. So normally at a CT, you try to do motion management, breathing management, or this the measurement of the breathing motion. And for that, 1 port is sufficient.
It is 3 minutes past, so we have to close this session. So Daniela and Khee, thank you very much for this interesting discussion, and of course for your presentations. And of course, I would like also to thank our audience, more than 1,000 participants. Again, this is great. So thank you